Hello and welcome to my presentation on the design and construction of a parabolic reflector antenna. My name is Dylan Lurch and I'm going to be walking you through the background research construction process and the challenges that I faced working on this project, as well as the future research that is available with both my project and in this field. So now for a quick overview of the contents of this video presentation. I'm going to be giving a brief background on antenna design, specifically parabolic reflector design and reflector antenna design. I'm also going to talk about my particular design and the design choices that I made. In part two, we're going to talk about the construction process and the experimental design. So I designed an experiment to run on the antenna in order to verify that it would work. Finally, in part three, I'm going to talk about the challenges, lessons learned, and the future research, both with my project and in the field. The first topic for my background research was antenna design theory. Antennas are the interface between the invisible wave frequency spectrum and our technology, and they're critical links in the satellite communication system. Antenna design is typically separated into two categories: transmission and reception. An individual antenna can be used for both purposes, but this is not always the case. Antennas are typically purpose-built depending on the system requirements, i.e. wavelength, gain, output, or other measurable quantities. One such type of antenna is the reflector antenna. There are several different categories within the group of reflector antennas, which include angled reflectors, right parabolic reflectors, parabolic dish reflectors, and just flat plane reflectors. As you can see on the left, these are the flat plane reflectors. You have the corner reflector, or it's referred to as an angle reflector, and you have a front feed and a center feed parabolic dish reflector in this particular diagram. There's also several different feed mechanisms, as I mentioned. There can be front feed, offset feed, and also center feed, and that's just for within parabolic reflectors. So within reflective antennas, I decided to focus on the parabolic reflector. And even within the category of parabolic reflectors, there are several subsets of different designs. And even within those designs, there are different types of feed mechanisms, like I mentioned earlier. The parabolic reflector, as you can see, uses a parabolic geometrical shape. So either in this case you have a full paraboloid, and in this case you have a cylinder that has a parabolic curve to it, and that helps to redirect all of the incoming signal that hits the face of the reflector into the feed. So here we have a dipole feed for the right parabolic cylinder, and here you have a front feed. So a signal will come in and be reflected off into the feed. So some common configurations are, like I said, the right parabolic cylinder, front feed, center feed, and offset feed parabolic dish. So some common uses, and one of the reasons why I was interested in this particular type of antenna are as satellite ground stations. So a lot of ground stations that are tracking satellites use this type of antenna. It's not the only one that they use, but this is often used. And it is also particularly often used in radio telescopes. As you can see here, this is a, I believe, 500-meter diameter radio telescope that was built in China relatively recently at 2016, I believe. And that is used to be able to capture these radio frequencies that are coming from outer space and need that large of a diameter in order to get a strong enough signal. Also, one of the most common uses for the parabolic reflector is direct-to-home TV. So I'm sure maybe you have or have seen a dish TV satellite antenna, and those are parabolic reflector antennas as well. So this is an overview of the design that I came up with and the design that I used to model my actual um, product after. So as you can see, it is a center feed parabolic reflector dish. It has a diameter of 7 3/4 inches. That is based on the fact that I'm building the dish out of a flat piece of sheet metal that was a maximum of 8 inches in diameter. Some of it is lost in the bending process in order to make it into the parabolic shape. I also designed it to be able to fit off-the-shelf components. So right here you can see this is a little channel for me to be able to fit in a receiver horn and LMB for a TV antenna, and this is based off of several experiments that I found both on YouTube and one that I found in a research paper. In order to be able to actually convert the signal into something that I would be able to view using my computer, I would also be purchasing a universal RTL SDR, and basically what that does is it converts the signal that you get from your LNB to something that the computer is able to use via coaxial cable, and it just plugs into your computer or whatever you're using to process the signal. So here again you can see my design in the front right and top view as well as an isometric view. This is the engineering, these are the engineering drawings of my design. So as you can see, this is the support structure right here that holds it up, and it's mounted via this screw hole right here to a standard desktop camera tripod. Right here, as I mentioned earlier, this is where the LNB connects and receiver horn, and this is the dish itself. The next section is the construction and experimental design portion of the project. Before I started on the actual construction portion of the project, I made sure to prototype my design and also plan out how I was going to use the materials and tools that I had in order to best meet the project requirements and to avoid waste. As you can see here in this image, this is a paper model that I made. The reason why I used paper was because sheet metal comes in sheets like paper, and the processes required to bend and shape such a material are similar, although not the same. And yeah, as you can see, it's mounted on the camera frame like the final product. After I designed and constructed a prototype that I was happy with, I decided to go ahead and make a paper template in order to help with the cutting portion and to make sure that the tolerances stayed relatively consistent throughout the construction process. So as you can see here, I have the template taped onto the plate that would eventually become the receiving dish. As you can see, it has the outside 8-inch diameter, which will be final 7 3/4, and then it has a 2-inch cut at another circular radius. And the reason why I did this is because in order to create a circular object out of a flat one, you can either, with metal, you can basically cold forge it, but I don't have the tools or expertise to perform that. So the other way you can do it is by cutting relief cuts into the metal and then folding them on top of each other. And that way you create a polygon, and if you have enough sides of a polygon, you have essentially created a circle. So the next steps are to cut out the main shape. So you can see that here with tin snips, and to also cut out the bending relief cuts, which you can see are also cut out here and here. And so that is basically just done with tin snips, which are essentially scissors for metal. And then the edge was refined with a sanding disc on a grinder, just to kind of keep that outside diameter consistent with the design. So then each of these portions, which I refer to as petals in the video and paper, are folded over each other in a clockwise motion. And the reason why it's clockwise is to keep irregularities from forming on the outside of the dish and try and make it as circular as possible. So this portion was done just by bending the petals inward in a circular motion by hand and overlapping them one over the other. So the next part was to finalize the shape of the dish and to weld the different petals together. The welding was necessary in order to keep the dish to have each petal keep its shape, and that's similar to in the prototyping, just taping the pieces together, but it's necessary to keep the metal from bending back into the flat shape that it once was. So as you can see here, in order to achieve that, I used just these welding vice grip clamps to clamp each petal together where I had already bent them and overlapped them. And then I welded them using a MIG welder. And I'll talk a little bit about the challenges in the construction process later. Here you can see I'm using a small ball peen type hammer to hammer the surfaces flat. That's because even with the relief cuts, there is some sort of binding and creasing. And in order to smooth out the inside of the reflector surface, to avoid not reflecting into the focal point, I used a hammer to soften out some of those creases. And then the final two steps of the construction process are to design the support structure, or I'm sorry, construct the support structure, as you can see somewhat here, as I showed earlier, and also fasten that to the dish via MIG welding, and to create the mounting hole here. And as you can see, it is mounted to the camera tripod. So because of some of the challenges that I faced in the construction process, I decided to also design a small experiment in order to determine the focal point and what I would do when the dish is operational in order to determine if it's capable of receiving signals. So the first experiment that I designed was to determine the focal point, and the way that that is done is I found an equation for the theoretical focal point of a parabolic reflector, and I plugged in my dimensions, but because of the nature of it being fabricated by hand, there are some inconsistencies, so theoretical focal point is not necessarily where the actual focal point is. So in order to find the actual focal point, I devised an experiment which uses laser projection and basically trial and error using using a laser to reflect off of the surface and determine the focal point that way. The second experiment was reception testing. So basically, I was going to use a laser again and connect it to the software and all of the other equipment and my computer and determine if it could actually detect a change in frequency. Because of the small size of the dish, it's unlikely that it would be super sensitive, but I will talk more about that in the future research section. The third and final part of my video presentation is the challenges, lessons learned, and future research. So some of the construction challenges that I faced were based on the material design and material choice, as well as the use of specialized tools and skills. So what do I mean by material design choice? So using sheet metal may not have been the best design choice within this project because it was um, more difficult than anticipated to create the parabolic reflector shape out of the um, sheet metal. And also, as you can kind of see in the images, even though I used some different methods to try and reduce the amount of inconsistencies there are on the surface of the reflector, it was very difficult to completely remove those without just using a completely different type of um, material. Also, because of the material, I needed to use a relatively thin gauge or thickness of steel, sheet steel, and this caused problems with the fastening method. So, um, for any of you that have welded, welding sheet metal is difficult, or at least it is for me because I don't have a ton of experience. Um, Working with such thin material, it's easy to burn through, and it's important to practice and use you adjust the welder accordingly. Um, and as I mentioned earlier in the design considerations, in order to make it out of sheet metal, I would have needed to use like a jeweler's sandbag, a torch, and um, a small wooden mallet in order to actually like just stretch the metal into a parabolic shape, and that also could cause inconsistencies. So it's something that needs to be investigated further to determine if there's better methods for um, creating this, uh, whether it be personal or commercial. And in addition to the construction process, the testing process and also posed some hurdles in this project. Unfortunately, as you can see from the final product, the receiver horn and LNB are missing because I purchased two separate um, products in order to serve that purpose, and one of them was non-functional and the other hasn't still not arrived in time for me to use, which is very unfortunate because I designed the experimental portion of the project to be able to use that information. Um, so without that, I was not really able to find a concrete way to determine the exact focal point for the most optimal signal reception, and it was impossible to record results. Um, I was able to use the open source Linux software that is mentioned in my research report in order to receive radio frequency signals and process them into something, a visual product that you can use to monitor frequencies, but it was basically useless without the antenna. So that's something that we need to also still be investigating. So finally, the future research, and this is just an extension of the challenges that I faced. Essentially, actually doing a test with the laser pointer to place the feed horn and LNB at the focal point. Um, again, I was able to use the software, but using the software to actually process the signal. Um, and the future research that, or the future iterations of this project would be to develop an automated aiming system. So that way, if let's say you wanted to actually be able to connect to a certain signal, let's say a weather satellite or something like that, you would need automated aiming because the manual aiming with just the uh, camera tripod is fine for uh, just doing these basic tests, but in order to set up something more professional, it would need a more fine-tuned and automatic system. Next would be scaling up the actual project itself. So, as I mentioned earlier, the dish itself is relatively small and would not be uh, very suitable or practical uh, for real transmission or reception. Um, and really, what it is just a proof of concept that personal satellite dish could be constructed, and also another portion of future research that could be conducted would be to test it against different types of reflector antennas, so um, the angle antenna and those other types mentioned earlier. Here are the references and resources I used to develop my project, in case any of you all are interested. And thank you all for watching. Good luck with your future classes and careers.